Welcome to this video. My name is Haonan from the School of Cyberspace Security, Hainan University. Our team is dedicated to researching intelligent connected vehicle safety. In this video, we are going to introduce our paper, an overview of Sybil attack detection mechanisms in VFC. Vehicle ad hoc network is an open mobile network consisting of vehicles and related infrastructure, which relies on wireless communication and sensor networks. Vehicles communicate with each other or with roadside units based on wireless LAN technology. The mode of communication in VNet typically includes vehicle-to-vehicle or vehicle-to-infrastructure communication. VNets mainly rely on cloud computing services for communication, computing, and storage. The tremendous growth in the number of networked vehicles and their increasing mobility has created a demand for low latency and uninterrupted service. Therefore, vehicular fog computing has been proposed to overcome the efficient communication and computing challenges brought by the emergence of the latest vehicle applications. In fog computing, fog servers are deployed on the network's edge, providing users with data storage, computing, and wireless communication. The vehicular fog computing network model consists of three layers: the mobile node layer, the fog service layer, and the cloud layer. In the mobile node layer, vehicles use WAN board units to exchange and store vehicle information via dedicated short-range communication technology. About the fog service layer, the fog node in the fog service layer can be roadside infrastructure or vehicles. The fog nodes receive information from the vehicles, then process and store it. In the cloud layer, the cloud server distributes tasks to fog nodes and receives feedback from fog nodes after the task has been processed. But like VNets, VFC is vulnerable to specific security threats, including trust, authentication, network security, privacy, and access control. One well-known threat is the Sybil attack. The Sybil attack is an attack on a computer network service. Attackers subvert the reputation system of the service by creating many pseudonymous identities and using them to gain a disproportionately large amount of influence. In the vehicle network, malicious nodes disguise normal vehicles to join the vehicle fleet and fabricate multiple false Sybil nodes to spread fake information in VNet. Therefore, the Sybil attack may affect the driving state of vehicles in the fleet. Before us, there are many articles summarize the structure, system, and security requirements of vehicle fog computing and discuss the security research of Sybil attack detection in vehicle fog networks. But their focus is more on Sybil attack detection in VNet. Most of them do not analyze the possible security threats and impacts of Sybil attacks in VFC, nor do they make a comprehensive comparison and summary and comparison of Sybil detection mechanisms in VFC. Even though some have proposed that some of the Sybil attack detection schemes in VNet are adaptable in VFC, no specific analysis and recommendations are given. Therefore, in our paper, we summarize different types of Sybil attack detection mechanisms in VFC for the first time, and provide a comprehensive comparison and analysis of these schemes in terms of traceability of malicious vehicles, privacy protection of normal vehicles, and resistance to attacks. We summarize the possible impact of 4 different types of Sybil attacks on VFC in terms of routing, vehicle decision-making, voting, and reputation systems, etc. We analyze the challenges of future research on the detection mechanism of cyber attacks in VFC. We also propose relevant recommendations and solutions for the research of detection mechanisms in computation, storage, and cross-domain authentication. Cyber attacks cause denial of service attacks, black hole attacks, selectivity forwarding attacks, and replication attacks, etc. By fabricating or stealing legitimate identities in VFC, due to the limited computing and storage capabilities of fork nodes, it is easier for attackers to initiate cyber attacks on them. We analyze the impact of 4 possible cyber attacks in VFC. Data falsification cyber, data reply cyber, DOS random cyber, and cooperative cyber. Data falsification cyber and data reply cyber are the most common cyber attack methods, and attackers launch cyber attacks by forging or stealing valid beacons. DOS random cyber blocks the communication network by randomly generating many cyber nodes. DOS random cyber is a joint attack launched by multiple malicious attackers cooperating to expand the attack scope and further increase the detection difficulty of the detection mechanism. The possible impact of cyber attack on VFC is mainly in routing, voting and reputation system, aggregation of data, traffic congestion, vehicle decision, distributed storage, and DOS attack. In routing, cyber attackers interrupt routing protocols which rely on paths and links between nodes. In voting and reputation system, cyber attacks can create enough malicious identities to duplicate reports and then remove legitimate nodes from the network to falsify voting results. In terms of data aggregation, cyber nodes may report erroneous sensor readings, which can affect the accuracy when aggregating vehicle data. Cyber attack also can make traffic congestion. Malicious vehicles can create the illusion of traffic congestion by creating any number of non-existent vehicles for the purpose of occupying a particular road. About vehicle decision, malicious nodes inject false speed or location information into VFC to influence the decision of surrounding vehicles, which causes them to suddenly accelerate or decelerate, resulting in traffic accidents. In distributed storage, cyber attacks can cause massive data damage in a distributed storage network since the data will be subject to virtual nodes. Apart from the above, cyber nodes launch DOS attacks to the fork node, resulting in the paralysis of crucial services. We summarize the existing cyber attack detection mechanisms in VFC into 8 categories. They are based on RSSI, based on machine learning or deep learning, based on blockchain, based on authentication, based on reputation, based on privacy protection, based on traffic flow model, and based on entropy. We made a comprehensive comparison of these mechanisms. From this table, we can conclude that RSU-based detection schemes are overall better than non-RSU-based detection schemes in terms of their ability to trace malicious nodes and protect the privacy of normal vehicles. The reason is that RSU-based detection schemes can avoid direct communication between vehicles through anonymization mechanisms or joint communication between ISU, which makes it difficult for malicious vehicles to obtain the privacy information of normal vehicles. In terms of the ability to trace malicious vehicles, it is easier to trace unregistered malicious vehicles through request messages because the ISU-based detection scheme needs to register vehicle information with the trusted authority TA or private cloud server in advance. In addition to this, most detection mechanisms do not consider or fail to detect DOS random Sybil and cooperative Sybil. Most detection schemes perform well in detecting data falsification Sybil and data reply Sybil, but few consider that malicious vehicles can cause DOS attacks by creating a large number of Sybil nodes. This type of attack is fatal to detection mechanisms that rely on a good communication environment. And cooperative Sybil attack allows information to share among various malicious nodes, and such attacks have a greater impact on detection schemes that require encryption and cross-domain authentication efforts. Some detection schemes based on authentication mechanisms can resist cooperative Sybil attacks due to their assumption of having a full trust TA to store and distribute keys. Under this assumption, malicious vehicles in different regions cannot access key information, such as keys and registration required for the attack. Finally, we summarize the possible challenges and prospects for future research on Sybil attack detection mechanisms in VFC. There are three main challenges: DOS random Sybil attack challenge, cooperative Sybil challenge, and traceability and privacy challenge. By creating a large number of Sybil nodes, a malicious node can also trigger a DOS attack while executing a Sybil attack. Sybil DOS attack is one of the most serious Sybil attacks that can have a serious impact on detection mechanisms that rely on a good communication environment or rely on ISUs to process messages. By launching this attack, an attacker can increase the communication delay of V2V or vehicle to ISU in the detection mechanism, thus preventing the vehicle or ISU from obtaining valid message information and performing detection in a timely manner. This type of attack can be solved by implementing methods based on entropy serial or multiple fork node layers. In the cooperative Sybil attack, valid information such as identity or key obtained can be shared among malicious nodes to be able to forge a valid Sybil node identical to a normal vehicle. In detection mechanisms that require encryption and cross-domain authentication efforts, if the registration information and keys of multiple regions in that authentication system are jointly maintained by a TA or multiple SM, the attack can be extended in a short period of time once a vehicle in one region successfully obtains valid information such as identity or key. To solve this problem, temporary communication keys can be assigned or more complex key management mechanisms can be adopted. In the non-ISU-based detection mechanisms, the detection of Sybil attacks is done by the vehicle at the fork node. Although this approach reduces the cost of equipment and improves the flexibility of the detection mechanism, it has significant shortcomings in terms of traceability of malicious vehicles and privacy protection of normal vehicles. This allows malicious vehicles to contribute to exist in the vehicle network and be able to steal the privacy information of normal vehicles to continue Sybil attacks. To address this challenge, the use of a vehicle registry or reputation mechanism can be considered. When the reputation of an unregistered malicious vehicle drops below a certain threshold due to forged Sybil nodes, it can be removed from the entire vehicle network. According to the available paper, we found that main reason why some types of detection mechanisms in VNet cannot be applied to VFC is its complex authentication mechanism or the need for strong computing and storage capacity. In order to improve the computing and storage capacity of fork nodes in VFC and solve the complex cross-domain authentication mechanism, we propose three solutions: packed vehicle as fork nodes, vehicle call detection, and blockchain assistance. Some also have proposed a scheme that aggregated the computational and storage resources of vehicles parked on the roadside to provide service for mobile nodes. In this solution, vehicles parked on the roadside or vehicles parked temporarily due to congestion can serve as fork servers to provide service to mobile nodes. As a result, the fork node expands from a single vehicle or ISU to multiple vehicle groups. For vehicle call detection, a vehicular edge computing fork-enabled scheme has been proposed. It allows offloading intrusion detection text to federated vehicle nodes located within nearby formed ad hoc vehicular fork to be comparatively executed with minimal latency. A call scheduling system that recommends suitable fork nodes for executing IoT applications and managing load in the cloud-forward environment has been proposed. And a dynamic resource orchestration scheme has been proposed to harmonize resource allocation for connected vehicles by migrating the offloaded service among fork nodes. In the future, the collaborative detection of vehicles can be applied to Sybil attack detection to reduce the latency of fork nodes in processing data and to improve the computation and storage capacity of fork nodes. It makes the complex detection schemes with higher security expected to be implemented on fork server layer. In addition, a flexible custom blockchain architecture has been proposed. The blockchain system is deployed on decentralized fork nodes, which enables decentralized and efficient cross-domain authentication. By implementing blockchain assistance, the vehicle registration and the key information is no longer maintained by a single TA, but by multiple regional SM. Each regional SM jointly maintains a public ledger, which can effectively resist the attack of tampering with the data space managed by one central authority. In addition, the sharing of information among SM can effectively reduce the communication overhead between vehicles and SM, and enable cross-domain access to vehicle registration and authentication information, thus effectively solving the problem of registration of vehicles across domains. But care must also be taken to resist the effects of cooperative Sybil attacks. So, in our paper, we summarize the different types of Sybil attack detection mechanisms in VFC for the first time and provide a comprehensive comparison and an analysis of these schemes. In addition, we also summarize the possible impacts of different types of Sybil attacks on VFC. And finally, the challenges and prospects of future research on Sybil attack detection mechanisms in VFC are analyzed. The above is the introduction of our paper. Thank you for watching.